that special time again when we take a break from the science and the engineering and the materials and the manufacturing and talk of something else. So a very simple one today, sort of a childish one, but I thought it was a very nice, decent one. There is a school child, any year 5, year 6, whatever. He is not generally very good in studies, and now today is his results day. So he comes back from the result, his report card is here. Now he has to go and tell his papa, his father. He goes to the father. Father, if I tell you that if I passed every course, what will be your reaction? He said, oh, I will go crazy with happiness. He said, by God, father, wallahi, if I pass every course, what will you say? What will you do? I will go crazy, I will go mad with happiness. Father, just because of that reason I failed. Back to manufacturing and science, right? So we had already done until some stages, right? That this is the drawing stress, the average flow stress is this, and for the maximum value where the drawing stress can be equal to the flow stress, this is the equation. So if we take y bar epsilon 1, right, y bar multiplied by epsilon 1 and equate it to k epsilon 1, so this is the equation. So now if you see k epsilon 1 n cancel out on both the sides, n plus 1 can go to the other side, so epsilon 1 is equal to n plus 1, right? So now this is very simple, but this is the elegance of the solution, that this is it. Here you were thinking of the physics or the mechanics of the problem, and then it is okay. Now epsilon 1 is ln a naught by af, right? Maximum reduction, of course, is a naught minus af upon a naught. So the maximum reduction per pass, this again, remember, when you do a naught upon a naught, it is 1 minus af upon a naught, isn't it? So from here, if you take ln, right, e raised to this, if you take e raised to this, so e raised to epsilon 1 will be a naught upon af, and opposite of that af upon a naught, because from here it will be af upon a naught. So opposite of that will be the e raised to epsilon 1 upon that, right? So that is it. Maximum reduction per pass is a naught minus af upon a naught, which is equal to 1 minus af upon a naught, and af upon a naught is 1 upon a naught upon af, which you find from there by taking e raised to this, e raised to this. So here we find 1 minus e raised to minus n plus 1 from here, right? So this you can do very easily. So this you have now found that the maximum reduction per pass for a material which has a strain hardening rule is this much, right? So now if n is equal to 0, they say for a perfectly plastic material n is equal to 0. You see, a straight line is a straight line, this is the elastic region, and then n is equal to 0 is the flat line. Otherwise, for n is some value, it goes up as a curve. So n is equal to 0, it is a perfectly plastic material. So put n is equal to 0, what do you get? 1 minus e raised to minus 1, which is 1 minus 1 upon e, which is the same expression that you found in the previous example. So this reconfirms that your physics and maths is totally correct, isn't it? Because a strain hardening material you have found, this is the more general case. If in a strain hardening you put n is equal to 0, then it means there is no hardening, which means it is perfectly plastic material. So if you put n is equal to 0 in this solution, it reduces to the same solution that you had for the perfectly plastic material. So this is reverse engineering, right? This is a proof that your work is right. So these two last problems, the maximum reduction per pass for a perfectly plastic material and the maximum reduction per pass for a strain hardening material, these are also simple math, but with some physics or mechanics understanding at your back, only one line of understanding, and then you are okay. And of course reduction is a naught minus af upon a naught. change in area upon original area is the reduction in area. So that is very simple. Okay. So we have done, in the first time, we did a numerical problem for finding power and this and that. This is the ideal work, this is the friction work, this is the reduction. So that was an actual numerical work of finding forces and pressures and those type of things which are in actual wire drawing or rod drawing. And this one, that you can predict or you can find out that if my reduction is more than this percentage, then I should not do it in one go. Otherwise, some tools can break, or at least my material can crack and so forth. So therefore, if this is the maximum value, then reduce that. Do it in 2 stages, just like we did in forging and rolling and so on. Okay. So you are now very strong in both the general understanding of how rod and wire drawing is done physically, and how do we apply the simple mathematics of it to solve problems. Drawing of a flat strip. Remember, this is now totally different. Until now we were doing round cross section, circular cross section. Whether it is a solid rod, very thin solid rod is a wire, or whether it is a hollow rod which is a tube, they are all circular cross sections. But if we are doing drawing but on a flat strip, there is a rectangular piece and we are trying to pull it through the die by drawing, right? So now, drawing of flat strip as compared to round sections. Now drawing a stress for ideal condition. Flat strip is a plane strain condition, remember. If it is a round piece, remember we are doing it from forging and so on. If it is a flat piece, we can do a 2D view and we can do a plane strain. In plane strain, we don't have y, we have y prime, right? The plane strain one. So because it is not a round cross section, therefore we can do that, right? So sigma d is the same equation. Sigma d is y ln, right? But here, rather than a naught upon af, because it is a flat strip, therefore t naught upon tf. Rather than reduction in area, you are finding reduction in thickness. So that is it. And instead of y, you have y prime because of plane strain. And this prime, remember, is upon 2 upon root 3, 1.157, that type of thing, right? So that is it. So the same equation, original equation was y ln a naught by af. This time, because it is a rectangular cross section, it becomes y prime ln t naught by tf. Okay. Now maximum reduction per pass can be obtained by equating the drawing stress to the uniaxial yield stress of the material, just like earlier. So y prime ln t naught by tf is equal to y, because this can have a maximum value of 1, right? So ln t naught upon tf is y upon y bar, right? And we know that this y dash is 2 by root 3 and so on. So this number is root 3 by 2. Therefore, t naught by tf, take e raised to this and e raised to this. So t naught by tf is e raised to root 3 by 2, and maximum reduction per pass is 1 minus, right? Remember, t naught by tf or tf by t naught is 1 upon that. So it is 58% this time. I'm not explaining a lot here, because this is exactly the same as we did last time, with just the variation that a naught by af has become t naught by tf. So this time it is 58%. Earlier in a round one, it was roughly 63%, if I remember correctly, but you can go back and drawing of tubes, right? Until now, whether it is flat strip or it is rod or wire, it was solid in cross section. But tube means that there will be a mandrel in between. Remember, there will be a mandrel in between. So there is a die. If you want to do a tube, it is a cutting cross section, then there should be a mandrel. Right? So now you are pulling the mandrel with the material, and when the material is pulled with the material flows, but then the mandrel stops it here, so it can flow only in the gap between the die and the material and the mandrel, right? This is the die, this is the mandrel. So the material can only flow into this gap, and when it flows only into the gap, then it becomes tube, right? So A stage, B stage, C stage, D stage, and so on. So this B, this B is 1, and here we are seeing floating mandrel, right? The mandrel is not being pulled, it is called a floating mandrel, this is something else, and a moving mandrel is something else. But I am not going into the details of this, because how hollow sections are drawn through different types of die schemes in extrusion we have already told you, mandrel we have already explained to you. So here very briefly, that if we have to draw a tube, only thing is that we are pulling it, right? The force is not from here, the force is a pulling force, and then just go back and try to see how mandrels were fixed and how it was done there. So it is drawing of tubes is covered. With that, we have finished what we were going to cover with you today. There is another process, manufacturing process, the fifth in this chapter, called swaging. That is a very small coverage here, and it is not an operation which is done in most of the workshops or factories in the world. So I am dropping that, it's a very small topic. So forging, rolling, extrusion, drawing, these are the four major ones. So that is there here. Remember, I am not saying read it yourself, this is not included, swaging is not included. This part now, that the end of the chapter has these topics: defects in drawing, drawing practice, manufacturing methods of the die failures, and then economics of bulk forming. So you see, this is about drawing, only drawing, the process of drawing, what are the defects in drawing and what are the drawing practices. This is general for all, for forging, rolling, extrusion, drawing, die manufacturing methods, die failures, and economics of bulk forming. So these are very small topics which are about the whole chapter of bulk deformation, right? So again, I have done that extra work for you, that I have created the slides. So the summary is here, but the book is also there. Now the explanation will not be. So here the chapter ends from my side, right? But these slides are there: defects in die manufacturing methods, die failures, economics of bulk forming, right? So with this, we will come to the end of the chapter. This was a very long chapter, but you see, sometimes some books do that. Some books have individual chapters, one chapter on forging, one chapter on rolling, one chapter on extrusion. So then you feel very good. But in this book, they have put all of them together, because after all, they are all bulk deformation. You are not cutting any material, you are not melting any material. So therefore, this is it, and hopefully you have a lot of basic understanding. Of course, deep understanding will be only when you actually join an extrusion company or a forging company and so on. But basic understanding, that you understand the process, you understand how it is done, you know the general machines and tools and so forth, you know the mechanics, you know the mathematics, you can solve some problems about forces and pressures and power and so on, and you feel good, right? So thanks a lot for being with us, and we will inshallah see you next time. And please again try to cover the materials before any quiz is announced, before any exam is announced. Those parts of the chapter which are covered in the homework, please try to keep on doing that by yourself. Thanks a lot. We'll see you next time. Ma salama. Final end of chapter 6.